in the way of an introduction, priority search queues were introduced by Edward McCreight in his 1985 paper, Priority Search Trees. Now, I don't believe he used the term priority search queue in the paper, but he defined the abstract data type right there in the abstract, and the abstract data type came to be known under the name priority search queue, whereas the name priority search tree continues to be applied to the data structures that he presented. There was more than one. So what priority search queues are well, they're a combination of sorted maps. Sorted maps are found in Clojure, so as returned by Clojure core sorted map, with an additional ordering on values, in this context typically known as priorities, and I will henceforth refer to them as priorities. That is independent of the ordering on keys. In particular, a separate comparator can be used, but sort of messes with the key ordering. And so, in addition to the regular map function that you'd expect, like the search get subseq for sorted maps, right? Priority search queues also support an operation that in Clojure it is natural to call peek, which retrieves a binding with the minimum priority. It's okay for bindings to be tied on priority, so in that case one of them will be retrieved, right? One of those minimum priority bindings. There's pop, which is actually clear at this point, because if we have pop and dissociate, then of course we can, peek and dissociate, then we can of course first peek and then dissociate, but well, pop is such a common operation that it will typically be implemented directly for a little extra performance. There's priority seek, and I'm using a fresh name for this operation because this is a sorted map, and by sorted I mean it's sorted in key order. So if you call seek on the map, you'll get back your entries in key order. However, it's also possible, since we have peek and pop, to traverse it in order of non-decreasing priorities. So there's priority seek as a separate operation. And then where things really start to get interesting is with peek and key range. So in addition to being able to retrieve a minimum priority entry in the map overall, in the whole map, you can query for that just within a certain range of keys very efficiently. And finally, in addition to seek, subseq, rseek, rsubseq, which are all supported, priority search queues also support what I might call priority-bounded traversals. And the Clojure name I chose to use for this is seek less than or equal, and similarly for subseq and rseek and so on. So these are traversals over the specified key ranges that work as you would expect. They work like seek and subseq and friends. But they only return those entries whose priorities do not exceed a certain upper bound that you get to specify. In this case, lower priorities win, as is usual. So you get priorities no worse than a certain threshold. And of course, this is something that you could do with a sorted map by combining subseq and filter. The thing is that if you have a very large range that includes, say, a few thousand or a few tens of thousand entries, and there's only a handful of entries whose priority falls under the threshold, well, you're still going to have to walk the entire range if you combine filter and subseq to get your low priority entries. Whereas with this operation, the traversal is optimized and kind of prunes fragments of the tree away so that you can expect very good performance if there are only a handful of entries to retrieve. And so the net effect of this is that priority search queues support, well, they recognize two independent dimensions in the data set, and along the key dimension, they support full-powered search, as found in regular sorted maps, But on the other dimension, they support less powerful search, so that while on the key dimension you can specify 2 endpoints to range, along the priority dimension you limit it to specifying an upper bound, and so you sort of get to query your data structure for those entries that fall within an infinite rectangle of sorts, and it's infinite because you cannot provide the bottom boundary. So hence the name 1.5 dimensional tree search, right? It's search in one direction that's full powered, search in another dimension that's only half powered, and then you get to combine them. Now, there are several approaches to implementing priority search queues. McCreight himself introduced 2 in his original paper. His approach, well, the more generic or generally applicable approach of the 2 he described is based on binary search trees combined with a certain heap structure. So the idea there is that you build a tree, and that tree uses the very same nodes to support a binary search tree structure and a heap structure. Now, well, it uses the same nodes, but not the same keys. You can't use the same keys. So the nodes repeat some information, but overall, the invariants maintained by the various algorithms are such that you can very efficiently use both these structures to carry out all these operations. And what's interesting about the scheme is that it admits balanced BSTs as the substrate. In fact, there's some freedom as to which balancing scheme you can use. The one constraint that your scheme has to obey, though, is that the number of rotations that it uses to fix up your tree as you perform associates and dissociates and so on must be bounded by a constant. And this is somewhat unfortunate because most popular rebalancing schemes do not obey this constraint. AVL trees don't obey this constraint. Weight balance trees don't obey this constraint. Red-black trees, well, it depends. It's possible to implement red-black trees so as to obey this constraint, but for example, Okasaki's beautiful purely functional implementation does not. But if you choose one that does, then you get a very beautiful data structure that supports all these operations. In particular, it supports priority-bounded traversals very efficiently. So this is the original priority search queue data structure, but I'm not going to go into any more detail about it because I'd like to focus today on a more recent realization of the same abstract data type due to Ralf Hinze, who in his 2001 paper, A Simple Implementation Technique for Priority Search Queues, presented what he calls priority search penance. And now, some of the core ideas here are the same. So priority search penance also use a binary search tree structure combined with a heap-like structure. But the crucial difference is that in this case, this is not a full heap. It's only a semi-heap. And the difference is that a heap is conceptually a binary tree where every node dominates its 2 subtrees. Right? So in this case, every node has priority no greater than any of the nodes in either of its 2 subtrees. With a semi-heap, this condition is relaxed, and each node only has to dominate one of its subtrees. It may happen to dominate both, but it doesn't have to. And so this relaxation comes at a certain cost, and you can see here that priority-bounded traversals are more costly in asymptotic terms. Although you still, the R parameter here corresponds to the number of entries actually returned. So when it's small, you get logarithmic performance. As it gets larger, you get closer to linear, but you get closer to linear faster than you would with priority search trees. But then because there are no constraints on the rotation scheme, you can plug in something like an AVL tree or a weight balance tree or whatever you want, really, which is very nice. And additionally, this implementation technique that Hinze alludes to in the title of his paper is really strikingly beautiful. Sorry, I really had to implement this data structure, so I chose to go with this one first. Now, before I go into more detail on priority search queues themselves, there's one other data structure that I wanted to mention because it's a natural point of comparison, and that is Mark Engelberg's data priority map. So this is a library that's been available in Clojure contrib since 2010. It exposes a map type that's, well, mostly hash-like map, hash map-like, but it additionally recognizes a certain intrinsic ordering on priorities, on values, again, in this context known as priorities. And well, the way they're recognized is that peek and pop are supported efficiently, and additionally, your plain seek traverses the map in order of non-decreasing priorities. And all of this is implemented using a pairing of a regular hash map, regular Clojure hash map, and a Clojure sorted map that stores an index from priority values to hash sets of keys mapped to those values. And incidentally, this is an excellent library, and it's well worth checking out. I highly recommend it, and of course, Mark's name is a seal of quality in itself. So please have a look. If you need this particular feature set, then this is really an excellent choice. But of course, this is a hash map-like structure rather than a sorted map-like structure. It doesn't support all those extra operations to do with key ranges. So it's fantastic for when you need this particular feature set, but I actually want to have a proper priority search queue in Clojure, so that's what I implemented based on Hinze's approach in a library called PSQCLJ. Now, what PSQCLJ is, it's an implementation of priority search plans as described by Hinze. It uses Adams's weight balance scheme, partly because it's really a very pleasing scheme aesthetically, and partly because this is what Hinze uses in the paper. So I wanted to implement the same thing and then potentially experiment with some modifications. It supports what you'd expect. So again, there's get, assoc, dissoc, all the seek variants. You do get peek and pop. You do get priority bounded traversals. There are independent comparators for key and priorities, for keys and priorities. But then, in addition to that, well, you may be, for those of you who are familiar with data-IVL, which is a contrib library that I wrote, data-IVL provides sort of maps and sets that are like those in Clojure, but based on IVL trees, which leads to very favorable performance characteristics. But additionally, they also support a range of additional operations. And really, the core of data-IVL has on that is that it aims to take balanced binary search trees as far as possible and supports all the various interesting features that they are capable of supporting. So similarly here, I wanted to get the ADT as rich as possible, and so PSQCLJ priority search queues also support nth. They also support rank, which is the inverse of nth. They support split and subrange, and we'll see shortly what that means. But roughly, it means that you can slice them so as to discard entries that fall outside a certain key range, and then you get back an independent priority search queue. And since we have subrange, we can combine peek with subrange to get peek in key range, mentioned earlier. This is not an operation Hinze actually mentions in this paper, but well, clearly it's possible to implement it, so good. A direct implementation might be possible, but that will only be an optimization. So overall, these are data AVL-like priority search queues. They really offer pretty much the same abstract date type. I actually realized, this recently, already here at the conference, that I left out nearest, but nearest will be a very straightforward addition. So we'll get the same abstract date type plus priority search queue operations on top of that. And in use, this is what they look like. There are 3 constructor functions. So here's one of them that takes a collection of key priority, and so on, and returns a priority search queue. You can apply peak to it, and then you don't get the leftmost entry because, again, standard traversal is in key order, but you get the lowest priority, the minimum priority entry. You have your nth, you have your rank. Then, in addition to that, if you do want to traverse the entire data structure in priority order, well, that's possible. If you want to take a regular subseq over your structure, that's also possible. If you want to add a priority bound, that's what subseq less than or equal is for. Then subrange. So this is an example of subrange application. So subrange has the same interface as subseq, it's regular subseq. But what it does is it slices the original, right? And the return value is a completely independent priority search tree that only stores those keys and priorities that are relevant, right? So it doesn't hold on to any part of the original for GC purposes, except those parts that are actually shared and sort of usefully shared, if you will. And then split is a function that subrange is actually built on top of that splits your input priority search queue into a priority search queue of entries whose keys fall to the left of a certain bound, to the right of a certain bound, and then in the middle you get the actual entry at your specified key if present, otherwise nil. So here are some benchmarking results. Way to interpret these is that I used 0, 5,000, and 10,000 as test keys when performing the get assoc with a low priority, assoc with a high priority, and dissoc on a priority search queue, priority map, and a sorted map of 5,000 entries each. Well, it's a bit of a special case in setting them in order, but it's a good starting point for benchmarking. And then the final four benchmarks don't make sense for a sorted map, but they do for PSQs and for data priority maps. So as you can see here, on get, data priority map absolutely transfers the competition, which is expected because, again, it's based on a hash map, so no sorted data structure will ever come close. But then on assoc and dissoc, PSQ CLJ is kind of in a similar range. For assoc, it tends to do a little better sort of earlier in the tree structure here, but towards the end where we are associating to a missing key, it becomes slower. It kind of hits a worst case in the implementation. It's not going to get any worse than that. So maybe this can be ameliorated potentially with a different rebalancing scheme and maybe some other tweaks. But well, that's your worst case scenario. Peak is extremely fast because the winning entry is stored sort of directly. So there's really nothing to no search to perform. But then also pop is also very fast. At least here on this particular input. But then if you actually traverse the whole structure using priority seek, well, data priority map does somewhat better. So I suppose depending on exactly what you want to do on the exact performance profile that you'd want or need, well, you may want to use one or the other. And in any scenario where they're both potentially applicable, it would be good to benchmark with both. And that should be easily done because they drop in inflations for each other when it comes to the shared functionality. But at least in some composite benchmarks that only touch that shared functionality, PSQ-CLJ actually comes out ahead. And now this final simple Dijkstra benchmark, well, I don't have the code for it here or the input data set. It's a fairly small graph, and the benchmark applies a fairly straightforward implementation of Dijkstra's shortest path algorithm to find all shortest paths from a certain vertex. And I have to say that that despite using criterion, I found that variability in results, so the variance in these results is a little higher than I'm used to. So it's entirely possible that the actual performance gap is smaller than this. But you know, even if this were a bit of a fluke, it's at least possible, right? So PSQ-CLJ gives you a richer data type, and at least in some composite usage scenarios, it may still come out ahead performance-wise. So I'm very happy with that. So this is a sort of a short comparison with some points that are very clear. The other points are maybe in need of more research. So with PSQ-CLJ, you get richer ADT, you get proper constant time peak. Data priority maps peak is logarithmic time. Now, as Mark explains in the docstring on the namespace, that's probably fine in many scenarios, but well, it's just something to take note of, I suppose. Additionally, PSQ-CLJ has a consistently sized data structure, if you will. Data priority map can be very compact in some scenarios, but it can grow larger in others. But then with data priority map, you do get that at hash map speed. So if you perform a lot of lookouts and you don't care about any ordering on keys, then well, probably that's the way to go. Now this comparison doesn't include data priority map because it would make sense to include it because it doesn't recognize any ordering of on keys. Well, I thought it might be interesting to compare a priority search queue of 500,000 entries to a sorted map with the same 500,000 entries. And see how well they do on priority-bounded traversals. So with a regular sorted map, I just have to compose filter with subseq. That's the only way. And these numbers lower down 157, 54 milliseconds, depending on whether we use the comparator or a slightly optimized version with an actual numeric comparison. We take 50 odd milliseconds to find the one entry in this range of about 34, I think exactly 34,000 entries that has a low enough priority to be of interest, right? That's 150 milliseconds, roughly. In contrast with a priority search queue, the same operation semantically takes about 27 microseconds, right? That's more than 3 orders of magnitude, so roughly 3 orders of magnitude better than a sorted map. And so this is perhaps the set of numbers that I'm most happy about in this presentation. And I think it establishes that, well, if you have use for these particular operations that these data structure supports, then yeah, you may want to have a look, and they're actually eminently usable, and they offer excellent performance. All right, so this actually concludes the section of my talk that focuses on user visible concerns, if you will, the public API and so on. I do have a sort of a to-do slide at the end. I might get to that with some planned features. But when it comes to what's there right now, this is it. These are the preliminary benchmark results. And if you want to check out the library, it's available on GitHub. It's available on Clojure. I'll have the references on the final slide. But I don't want to wrap up quite yet. Instead, I think it might be interesting to peek under the hood and see how all of this happens. And the key insight here is very cool, I think. So, okay, so what we want to do is we want to store a bunch of key priority entries in such a way that access to low priority entries will be very efficient, right? But we can also perform all the sorted map operations. So imagine, if you will, that the entries are contestants in a notional tournament where each key arrives with a priority in its hand. And they face off in matches. It's a single elimination tournament, so whenever a key loses a match, it gets eliminated from the tournament. And as you might expect, the winners are those keys, or those bindings that have lower priorities. So this diagram here depicts a tournament like this. There's purple. No, I think it was going to be purple. It looks sort of brownish. So there's this brownish node here, who's the leftmost contestant. So this key comes first in key order. It faces off against the red node in its first match, and it gets promptly eliminated because, well, I suppose the red node's priority is lower. So the red node progresses onto the next round. And then in parallel with that, conceptually, the teal node faces off against the blue node, and the blue node wins and progresses onto the next round. And then we play another match between the red and the blue node. The blue node comes out on top and becomes the champion, right? And so this kind of structure is called a tournament tree, and it captures the structure of a tournament and exactly what happened in it, what the outcomes of the various matches was, by placing contestants in leaf nodes and annotating internal nodes with winners of matches. Right? So this is a useful picture to have in mind, but it's not very helpful when it comes to implementing data structures like, to support PSQs, because, well, for one thing, it uses twice the number of nodes that are necessary, and it's generally not best suited to the kinds of manipulations that we're interested in. So Hinze suggests that we could do something else. So in the tournament tree, we annotating internal nodes with winners of matches, right? Now, of course, every match will be won by one contestant and lost by another. So how about annotating match nodes with losers instead? Well, this is what we do on the right. And the lower three nodes here correspond to the top three nodes in the tournament tree. And if you compare the two diagrams, then, well, here we see that the first match was won by the red node, but lost by the brown node, and so the brown node occurs down there in the leftmost node of the so-called pennant. The teal node lost its match against the blue node, so it occupies the rightmost position. Then from the left subtree, red node emerged as the winner, right? But then it faced off against blue and lost, so it becomes a loser at that point, and we annotate the middle node, so the top node of the triangular fragment, if you will, with the color red. And considering the fact that in a single elimination tournament, every single contestant except for the overall champion loses precisely one match, and every match is lost by precisely one contestant, this triangular portion of the diagram, comprising the brown, teal, and red nodes, contains all our contestants but one, right? And the missing contestant is the overall winner. So it's not stored in the tree, but that's no problem, right? Because we can just add it on top. So there it is. And perhaps if you squint a little bit, you might see how this can be taken to resemble a pennant, right? So that's where the name comes from. And what bears mentioning is that as expected, as promised, this is a semi-heap because each loser will have made it to that round by winning some previous matches, right? So red lost its match against blue, and therefore it's stored in the loser part of the diagram, but it still previously beat brown, so it's not stored at leaf level, right? It's stored a little higher up, and it dominates its left subtree, right? But perhaps not the red subtree, the teal subtree. We have no idea whether red would win against teal or not. And this is why it would be costly to maintain a heap structure instead of a semi-heap, right? Because we would have to play some additional matches and just do more work to determine whether these matchups that haven't actually occurred in the tournament would result in a win for this contestant or that one. And the way this is represented at runtime is roughly like this. This is not actual code. In fact, that's written, it won't even compile because of the type hints. But it gives you the right idea, right? So we have our pennant. The overall pennant is represented by a winner node. It stores the winning key, the winning priority, the entire tree of losers, which is a branching tree, right? It's a binary search tree. And then it stores another copy of blue key in this instance. And what it does, well, if you look at the def type up there, the field is called ubound. That stands for upper bound. And this is the maximum tree that occurs in the overall pennant. And hopefully the reason why we need one will become apparent in a second. And notice then that loser nodes store keys and priorities as you'd expect. They store a left and right subtree, which is also something you'd expect. They have a size field, and this is used for rebalancing and also for nth and rank. So it's just bookkeeping that's used to support some extra operations and the overall performance profile. It's otherwise not very interesting. But there's also a split field. And the split field stores a split key that we use to traverse the tree structure. So the way the way that these structures are used in practice is that we literally play matches, or if we're given an existing pennant, then to perform various operations, we first decompose it into pennants representing the sub-tournaments. Like if you think about it, if you take a pennant, then the winner will have one sub-tournament corresponding to one loser subtree of the top loser node, and then faced off against the topmost loser and won, right? The topmost loser, the runner-up, will have faced off against the winner and lost, but prior to that, it will have won its own sub-tournament. So it seems like there should be enough information to reconstruct the overall tournament, and there is. And the way this works is if we're given two pennants with the precondition that all the keys in the left pennant need to be no greater than the keys in the right pennant, then we can play a match between them to get something like this. So here again, blue beats red. So blue becomes the winner, red becomes the runner-up, and then the left loser tree here becomes the left loser subtree of the loser tree of this pennant. The right loser tree here becomes the right loser subtree of this pennant. And again, both winner nodes store upper bounds, maximum keys for the respective pennants, right? So the red pennant's upper bound becomes the split key of the new loser tree. And if you think about it, this means that all the keys that occur in the loser tree to the left of the red node, well, including the red node itself, actually, this is less than or equal to comparison, are at most equal to, but quite possibly less than, the upper bound of the left pennant. So if we use these split keys to traverse the data structure, we are guaranteed eventually to arrive at the correct keys. The thing is that the split keys are stored separately from the value keys, if you will, the priority keys. So while traversing the tree using split keys, we have to check at every step whether we've found the key we're looking for. So we do about twice as much work as we would with a regular BST, and therefore searching is a little more expensive. But these operations are very simple conceptually, at least. And when you have this kind of operation, then it becomes a breeze to implement things like search, the search, or what have you. For example, with a search, you repeatedly perform this decomposition in this direction, right? We start with a tournament, and we decompose it into 2 subtournaments. We use the split key to decide which subtournament then we need to recur into, and we do, and we then split that one, and so on and so forth. And eventually, we'll get we will have decomposed tournaments a logarithmic number of times to get to singleton tournaments at the leaf level of the tree, at the fringe. And then our new key may already be present actually in the data structure, so then we update the priority in that singleton and replay tournaments on the way up. Or else it might be an actual new key, and then we play a tournament of 2 singletons. We get the resulting doubleton tournament, and again we replay some tournaments on the way up. Amazingly, this can actually be implemented using a reified tournament view. So this is the truly beautiful aspect of Hinze's paper. It's a Haskell paper, but he implements the whole data structure in the paper. But to do so, he uses a technique based on intermediate representations that are sort of wired into the program using a Haskell feature known as views. Now, he uses a different syntax than the syntax that was eventually adopted in GHC, but it's only a superficial difference. And so he actually decomposes tournaments into left and right sub-tournaments, and his recurrence patterns are based on those tournament decompositions. So one big question to me was, well, can this work on the JVM, right, with any sort of efficiency? And amazingly, it can, right? It's really very encouraging. And what's also interesting is that I had this idea that, it couldn't possibly be the best we can do. Because of course, this approach means that we're allocating all those intermediate tournament representations while performing associates, dissociates, and so on. So it might be preferable to just have, say, a single mutable argument and kind of manage our own calling convention by replacing some fields, and then some intermediate values that need to be stored will be stored in locals and eventually restored and so on. So that's the match frame approach. And I implemented both, and I compared them. And it turns out that, okay, well, the mutable approach is indeed a little faster for pop. It's about a tie for assoc, which is already surprising. Well, why is it only a tie? But okay, well, if it's a tie, then fine. Then at least with a mutable object, we're allocating less, so probably it's good to go that way. But then it turns out that for dissociates in my benchmark so far, the mutable object actually makes things slower. So it's not wired in currently. Amazing. Well, I'm definitely planning to benchmark this some more, but it turns out that this view-based approach is actually eminently workable on the JVM, so that's another major discovery here. Now, I wouldn't say that the test suite is complete, but it's already very extensive, and I'm very happy with the basic approach, which is that, well, the first thing I do when implementing a data structure these days is always the same. If it's at all similar to any existing Clojure data structures, I take collection check, I wire it in, and then I get a fairly high level of assurance that it actually matches the core of the interface it's trying to implement. But then everything else I wanted to check about the data structure, I decided to test about the data structure. I tested using custom test check properties. And these properties were reasonably practicable. Check not only the observed behavior of the data structure in the sense of return values and so on, but it is equality of return values, hash values of return values, and similar outwardly visible features, but also the internal invariance of the data structure. And the reason why I think this is important is because internal invariants have a sort of a double purpose in life. They partly ensure like the basic correctness of your operations, sure. So if you just test observed behaviors, then that's good enough to confirm that your invariants are being maintained insofar as breaking them would influence that observed behavior. But if your internal invariants really serve to prop up your performance guarantees, then in a small test you may not notice that you're breaking something, right? And yet your data structure may become unusable over time if it lives for a longer while, right? In a running image. So hopefully PSQ CLJ will not have this type of problem. I also use this approach in data IVL, and in doing so created some extra work for me, but well, that's fine, again, because when the work is done, I will have a very high level of assurance that it's really, truly sort of beyond any kind of suspicion. And okay, well, is this done? Well, no, it isn't, not entirely. Like the original implementation was written in Clojure, actually, but the current implementation is written in Java. So I think this is fine. Like it's fine to have the core thing in Java and then to call into it from Clojure. But there's a third, sort of a middle ground approach where the wrapper object itself would be implemented in Clojure, and then it would delegate to some internal objects for top performance. For top performance, and I'd like to experiment with that. A Clojure script version will also happen reasonably soon. Additionally, in some places, for those traversals, I need to call concat or a concat equivalent. So I decided to just call the invoke static method on the class that the function concat compiles to. That's available since Clojure 1.8. But now, by no stretch of the imagination can this be described as part of the public API. Right? So I seriously need to stop doing this, but it just wasn't one of the interesting parts, so I haven't so far. Now, to use it, you actually have to pass in lazy sequences for things to make sense. Otherwise, you'll still get your full call tree right away, right at the point of first call. So if you want to see some lazy sequence instantiations in Java, then well, please have a look. You'll see just how hideous that is. There's one function missing from the data IVL ADT, namely nearest, so I'm planning to implement that. This data structure is already implemented to support arbitrary comparators for keys and priorities, but I haven't exposed the by versions of the constructor functions, so that's also a plan. And then there are several other sort of experimental directions. Reinstate explicit direction fields, for example, refers to how we establish which subtree the loser came from in those pennants. I'm not going to go into that right now because I'm out of time, but feel free to ask later. I already have a version where this is implemented, but I need to do some further benchmarking before I'm confident that it's worth deploying. And that's it. The library is available here on GitHub and on Clojure. Hopefully, it's interesting enough that you might want to have a look. And thanks.